Welcome to today's video. For the record, this is my sixth attempt at this video due to various interruptions and things like that, so hopefully this goes okay. So today we have a video about t-tests for comparing the means of two groups. That's going to be very important. We're going to be looking at two groups, a comparison of their averages in some way. There's two scenarios, one goal to distinguish between paired data, so matched pairs, and then two independent random samples. So in the one situation, paired data, matched pairs, we may have one population with one sample of something like that, or some experiment where the data is paired in a meaningful way. The independent random sample scenario, maybe you have two populations you're trying to compare, and you take a random sample from each, and then you're going to compare their averages. I can conduct a t-test, an appropriate t-test for a given scenario, and make a database conclusion. So we are talking about means, so we are going to use t-tests, just like we used t-intervals. And then I can use technology to run the hypothesis test. So problem one, this is about the USDA checking the effectiveness of E. coli methods of detection. So determining the level of contamination. So what we're going to do is we're going to take, you have two different, just a quick summary. You can read this for yourself here in a little more detail. You have two different methods, A and B, of determining the level of contamination. And each of them were used on 10 randomly selected specimens of a certain type of beef. The data is measured in millimicrobes per liter of ground beef for each of the methods. Each of the methods shown in the table, all the data is right here for us. So you can see, just so we understand this table, you have their 10 beef specimens here. For each beef specimen, you have two measurements because we have because each of the methods were applied to each beef specimen. So think of specimen as like a steak or a burger or something. You've applied method A and B to that piece of meat, and you are looking at the level of detection for A and B, and you are comparing them. That's what we're doing. So the question we're going to try to answer is there a significant difference in the mean amount of E. coli bacteria detected by the two methods for this type of beef? Provide statistical justification to support your answer. So when we see this, is there a significant difference or provide statistical justification? We should be thinking some sort of hypothesis test. Okay, so what are we actually interested in here? So this is called a matched pairs or paired data design. Matched pairs design. We have 10 randomly selected specimens and two methods applied to that. So these methods, these numbers you see here for, like, let's say specimen 1, 22.7 and 23.0, those two numbers depend on each other because method A and method B were both applied to the same piece of meat. So it makes sense, if method A and B are both valid detection ways to detect E. coli, it makes sense that these numbers should be pretty close. And clearly, specimen 1 had a lower level of E. coli than, let's say, specimen 10 over here. So they're different types, they're different pieces of meat. So maybe they've been sitting out longer, who knows, but like this one right here clearly has a higher rate of detection. The question is A or B better than the other? So obviously that's what you would like to know, right? Like if I'm trying to check for E. coli, wouldn't I want to know which of these methods is better, or if they're equally the same, if they're the same. So if they're the same, it wouldn't matter which one I use, but if one's better than the other one, I would definitely want to pick the one that has a higher average rate of detection. So that's what we're interested in. So since they are applied to the same specimen, we are actually interested in the difference between these two numbers. They depend on each other, so clearly it doesn't make sense to compare specimen 10 to specimen 1. So we shouldn't treat these as like two independent groups. Method A's data and method B's data. We shouldn't treat them as they're not independent. They're clearly dependent, and we don't want to compare a 46.8 here to a 23.0 here. That's just not what we're doing. We're trying to compare the effectiveness of A and B on that piece of meat. So we are interested in the difference in these two methods. So I'm going to we're going to look at these data as the difference in their detection. So we got to look at 22.7 minus 0.3, that's a negative 0.3 difference. This one is a 0.5 difference. This is a 0.3 difference. This is a 0.6 difference. Okay, so I'm going to pause. What does this mean, just so we understand? This means that for specimen 4, method A had 0.6 millimicrobes per liter more in a level of contamination of E. coli detection than did method B. Okay, so that is like that's just the difference that was observed. This is 0.8. This is 0.7, this difference. This is 1.2. This is 0.2. This is negative 0.1. And then this is negative 1. So we care about, for our hypothesis test, what we're interested in is this stuff right here. Okay, this data, these differences that we observe. Is one of these better than the other one? Okay, so what are our hypotheses? So we have a hypothesis test. We got to start with our, in order to, to write your hypotheses, you got to know what your parameter of interest is. So your parameter of interest here is the average difference you see. So it's the average of this little row, mu with the little subscript d. This is the true mean difference in detection levels between methods A and B. And we already established that we're doing it in this order, but I'm going to include that in here, A minus B. Okay. So what are our hypotheses? So when they start this experiment, think about what's going on here. Your null hypothesis is your initial expectation. So what do we expect to happen? Our initial expectation, when they start this, if these two methods are completely valid, which they are, or why would they be testing them? We expect them to be equally effective. In other words, the average difference we expect to be 0. Like method A and method B should work pretty well. So that's our expectation. What is the alternative? The alternative explanation, which we're trying to test, is we're trying to determine if there is some sort of difference. We don't know if one is going to be better than the other one, but we want to determine, or which one's better, I'm sorry, but we want to determine if one is better. So A might be better than B, B might be better than A, but in general, we just want to know, is this average difference we observe not 0? In other words, A is better than B or B is better than A. Okay? So this is going to be a two-tailed test. We have no significance level given to us, so we're going to set that as 0.05. And then we're talking about means, so we should be thinking about running a t-test at some point, and we have one sample, so hopefully when we get there, we'll run a one sample t-test. But let's go through it, and we got to check conditions to do this. So let's check some conditions. So what are the conditions that we have, that we know for a one sample t-test? So first of all, do we have a random sample? It is stated in the problem that we have a random sample of 10 specimens. That's stated in the problem. Number 2, we have to do some sort of normal check. Okay, so for means, what are your normal criteria? You have a few things you can check. First of all, you always start and you look to see, do I know anything about the population? Well, according to this introduction here, there's nothing in there about the population of either the readings for method A, method B, or the readings for these differences, the population of these differences. There's nothing in there. So we don't know if there's a normal population. The next thing we look at, if that doesn't work, is do we have a sample of at least 30? So according to this, we clearly don't. We only have a sample of 10 specimens, so that's not enough. So what do? When we have a small sample, so when we have if we don't have we don't know that the population is normal. We don't know that. And your sample size is less than 30, which it is. We check, and you'll remember this, a dot plot of our, in this case, what are we going to check a dot plot of? We're going to check a dot plot of these 10 differences we see here of our sample differences. So we have this dot plot of sample differences that we're going to draw right down here. And we need to check these for skewness. So let's draw this quick little dot plot. So we have a dot plot. It has a title right here. It says this is what we're doing. Dot plot of our sample differences. So it's got a title to it. Here's 0. Our biggest difference in absolute value is 1.2. So we should be somewhere right about 1 and -1. So we had -0.3s in here, 0.5s up here, 0.3s in here, 0.6s up here. It's just got to be a sketch, but it's got to be labeled. You have to show someone that you know what is going on. 0.7, 1.2, -0.1 is somewhere in here, and then -1 is out in here. Okay, so we look at these things, this distribution of these 10 values, and we look at them for skewness, and we don't see really much skewness going on. They seem to be relatively symmetric. I feel like I missed a data point in there somewhere. I think I missed 0.2. 0.2 somewhere right around there. There's my 10. So it's pretty symmetric. There's not a big skew. There's no like huge outliers of any type, any sort. So we shouldn't be too worried about this not coming from a normal population. So we would say, so you got to explain how you use this thing. So there's no big outliers, no major skewness, no multiple peaks. So we talked about peaks, like a normal distribution only has one peak right in the center, no multiple peaks. So what does this mean? It means it's reasonable to assume the population of these differences is normal. It's reasonable to assume it came from a normal population. So if we had major skewness or like multiple peaks or a lot of clustering, sorry, this pen's glitching on me real quick here. If we had multiple peaks or skewness, then we would be in trouble, and we would have to like kind of proceed with caution. So those are our first two conditions. This is fine. The dot plot's okay. The third condition is independence. You have to check those. So the third condition is we have n equals 10 specimens. That is reasonably less than 10%. So I'm going to write it like this. This means that there are reasonably more than 100 beef specimens in the population. So this is less than 10% of the population size. That's pretty reasonable. So like the E. coli contamination on one shouldn't influence the E. coli contamination on another. And then finally, we have the population standard deviation sigma of the differences. We don't know anything about the population, to be honest. So we don't know this for sure, is unknown. So since this is unknown, we will use a t-distribution. So over here, we can say that we have the conditions work okay, they check out. So we can use we have one sample t-test for, and what was our parameter? For the mean difference. So at this point, you could run this on your calculator. We're going to go ahead and enter your data into your calculator and use that. So I already entered method A and B into list 1 and list 2, so you can pause the video and do that. So we're going to go to our calculator and enter that data in. So I have my data for A here and for B here. We are interested in the difference between them. So if we go up to list 3, we're going to make list 3 list 1 minus list 2, and this is going to give us our differences that we did by hand on the table. So there's our observed differences in the two methods and the contamination levels, and we're going to run our hypothesis test using this data that we have in list 3. So at this point, we can sort of quit out to your home screen and go to stat, test, and go to t-test. You have a one sample t-test. These are only for proportions. We're not doing an interval. This is a t-test. So you go to t-test. Okay, this time you have raw data, so we're going to pick data. And we know our hypothesized mean is 0. Okay, where's our data? Our data is in list 3. We care about those differences. The frequency is just 1, not important. And then we pick our alternative hypothesis. Well, our alternative was not equal to. And then we go ahead and we hit calculate. Okay. So here's our data we have. We have X bar, we have S. So this is the information we need, plus one other thing that we'll write in a second. So we're going to take this, and this is part of our test that we need, our important information here. Okay, so we ran our t-test. We have our test statistic, which is t, 1.4563-ish. Here's our p-value. Okay, this X bar, what is that? That X bar is the sample mean differences. In other words, it's the average of those 10 numbers right here. It's the average of these numbers. And that average difference, so I'm going to put a little subscript D right here on this. That is the average difference in our sample was 0.29. The standard deviation, this is the standard deviation of those 10 differences we saw. So that's kind of like sample standard deviation of those differences. So we'll call that D. N is 10, that's our sample size. The last thing we have to add to this that your calculator does not do, you have to state the degrees of freedom since you're using a t-test. The degrees of freedom for a t-test on one sample is n minus 1, so it's 10 minus 1, 9 degrees of freedom. Okay, so at this point, we have everything we need. We just need to make our conclusion. Our conclusion is based on your p-value. So our p-value is right here. P-value is 0.179. We compare that to alpha. That's clearly bigger than 0.05. So what's our conclusion? Our conclusion is that this data we have is very likely to occur if there's really no difference. So in other words, there's probably no difference. We have no reason to believe that A or B is better than one or the other. So we have support for our null hypothesis because our p-value, our data occurs with a high probability under that assumption. So we make our conclusion. So our conclusion is since your p-value equals 0.179 is greater than alpha, which is 0.05, we do not reject the null hypothesis I'm sorry, this is so glitchy. I don't know why. Null hypothesis that I'm just going to type this. Since your p-value, which is equal to 0.179, is greater than 0.05, we do not reject the null hypothesis. We have evidence, which is your sample. The sample data suggests that there is no difference on average between the effectiveness of methods A and B. Okay? Sorry about that at the end here, this thing. So that's our conclusion. Our sample data occur with a high probability, so it's not rare. So our conclusion is that we have no reason to believe that this is not the case, where they actually have no difference on average. And when you look at it, really, the observed difference you had was 0.29. So there's really not much of a difference between the effectiveness in detecting E. coli for method A and method B. It's not not far enough away from zero for it to be statistically significant. So this is our conclusion.